So in this video I want to look at the idea of related rates. Related rates is another application of derivatives, and it may make sense immediately to you that a derivative represents a slope or a rate of change, so we can use them to relate rates. And that may not be immediately obvious, but I think it'll make sense when you think about what we're doing with it. The idea behind related rates is taking the derivative of an equation implicitly with respect to time, so that we can relate the way one thing in the equation changes to the way another changes with respect to time, not with respect to each other. So just a basic example, say we're working with the area of a square. The area of a square is equal to the side squared. If we take the derivative with respect to time, so d dt of a would equal d dt of s squared, and that's simply dA over dt equal to 2s ds dt. And that's just using our implicit differentiation. And we can relate these two rates of change, the area and the side, as they're related to time. That's the basic concept behind related rates. And the hardest thing that people run into with these are you get a word problem and you have to try to set up an equation to relate the rates that you're dealing with. So I have here a problem in the top left, so I want to work that and kind of talk about the ideas of how you set these up and how they work. So it says that a sand gravel plant, or at a sand and gravel plant, sand is falling off of a conveyor into a conical pile at a rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So let's take a step back, think about what this is saying. We have a conical pile, so a cone. We're filling it up. So we're really looking at the volume of a cone. So let me draw a picture to kind of help us visualize this. Since we're pouring the sand into the cone, I think it should probably be looked at upside down as the way you would see it in the gravel plant. So we have our cone, the base is a circle, and it's going up to a point, and we're filling it from the top up here. So what is the volume of a cone? We know from geometry that's 1/3 pi r squared h. So we need to look at what are we asked in this problem. We're told that the sand is falling off the conveyor into the conical pile at a rate of 10 cubic feet per minute. So that means that the rate at which the volume is changing is 10 cubic feet per minute. And a few things to notice with that. First of all, when you see the term rate, you know you're probably dealing with one of your related rates in that, but it won't always be that obvious. When you see cubic feet, what units do we have cubed? It's normally dealing with volume. So we know that the change of volume, dV over dt, is going to be equal to 10 cubic feet per minute. Okay, now it says that the diameter of the base of that cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So this 15 feet high is our h value. And it asks us what is the rate at which the height is changing. So we want to find dH over dt. So if we look at this equation, we have V, we have H. We have one problem in this. That r squared we can't deal with. We could take the derivative implicitly, but then we're going to have an r and we're going to have a dr dt, and we don't have a dr dt value given to us in this problem. And you'll see this a lot when there's 2 variables, 3 variables. You need to eliminate them where you're only dealing with the rate of 2 different things. But we're told that the diameter of the base is approximately 3 times the altitude. The diameter is this distance across the circle. The altitude is the height, h. So if we know that the diameter, d, is equal to 3 times the height, Well, our formula for volume deals with radius. Well, radius is 1/2 of diameter, so if we divide by 2, we get the radius is equal to 2/3 or 3/2 h. So we can substitute that in for this r squared in our equation to get a volume equation to work with in this related rate. So when we do that, we get our equation that volume of the cone is equal to 1/3 pi times r squared. We know r is 2/3h squared times h. And when we simplify that, it's 1/3 pi times 9/4, which is our just squaring 3/2, times h squared times h. And we'll simplify that again. 9 times 1 will give us 9 in our numerator, over 3 times 4, 12 in the denominator, pi h cubed, because when we're multiplying the two variables we add the exponents, and that simplifies because 9/12 is 3/4 pi h cubed. So this is our volume. So now that we have that, we can take the derivative of it with respect to time. So we want the derivative with respect to time of v equal to the derivative with respect to time of 3/4 pi h cubed. So we know on the left side that's quite simple. We'll just get dv over dt. And on the right side, 3/4 times pi is a constant multiple, so we'll just leave that there. The derivative of h cubed, just use our power rule. Pull the 3 down, drop the power 1. But since we're taking the derivative of h with respect to t, using implicit differentiation, we multiply by dh over dt. So cleaning it up some, we'll multiply the 3's together, and we'll get the rate of change of volume with respect to time equal to 9/4 pi h squared dh over dt. So now we've gone through that, we need to plug in our values for dv dt, for h, and then we can solve for dh dt, which is what the question was asking. So we know that we're told h is 15 in the problem, dv dt is 10, as we noted up here. There's 10 there, 15 here at the end of the paragraph. So if we plug 10 in for dv dt, 15 in for h, and then we just need to do the basic arithmetic to solve for dh dt. So we'll say 10 is equal to 9/4 pi times 15 squared dh over dt. Simplifying, we get 10 is equal to 9 times 15 squared, which is 225, times pi all over 4 times dh over dt. And to solve for dh dt, we'll divide by this here on the right side, or we can just multiply by its reciprocal. It'll do the same thing. And we'll get dh dt isolated equal to 10 times the reciprocal of this, which is 4 over 9 times 225 times pi. And when you simplify that, that is 8 over 405 pi. But remember, we're dealing with the rate of change, so we need units. What are our units? Let's look back at the original problem. We're dealing with feet and we're dealing with minutes. So the rate of change of the height will simply be feet per minute. And this is our related rate. So what we did in this equation was we set up a relation of volume to height, took the derivative with respect to time. That way we could compare the rate at which the volume and the height are changing in respect to one another. So this is a concept that you'll see in algebra, or I mean in calculus classes, and it's quite useful in a lot of different applications in physics and chemistry and economics. So it's quite useful. I hope this video helped you and that you can go out and apply your derivatives for a lot of really cool things.